Hi everybody, this is Kellen Billadu, and today I'll be going over Lab 4. So, our purpose is to understand the relationship between voltage, current, and resistance in various circuits, understand the placing of circuits in parallel versus in series, and explore RC circuits. So for the model, we use a bunch of different models in this one on an online tool. The system is the circuits. There are no surroundings in this online model. The assumption is that there are no other influences other than what is in the circuit, and that the wires and ammeters have no resistance, and that the voltmeter will have infinite resistance. So, and then the initial condition will depend on the circuit, and this applies to the RC circuit. So for the physical principles, we're looking at Kirchhoff's laws, Ohm's law, resistors and capacitors in series and parallel, capacitance, and RC circuit equations, all of which you can see on these graphics on the right. So preview the result. Because it's a generated model, the results exactly match what was predicted in the equations, at least to a very significant degree. Current chooses the path of least resistance, so if there's a wire in parallel with a resistor, it will choose the wire every time. RC circuits charge capacitors, increasing the resistance in the capacitor's path over time. Okay, so for the first experiment, we just have some resistors in series with an ammeter, and you do the calculation, and you get that the current is 0.02 amps. If you separate it and you put a voltmeter across the gap, it will be 3 volts because that is the EMF, and the potential across the gap is always going to be the EMF. And then if you do the potential across the segments, you'll see that from A to B it's 3 volts, B to C it's 0, C to D it's negative 0.96, D to E it's 0, E to F it's negative 2.04, and then the rest is 0. So then if you do V net, it's 3 minus the voltage drop across the resistors, and you get 0, and this follows the loop rule, right? So then you can see in this, right, it goes up across the EMF, and then it's constant across all the other ones except the resistors, where it drops by the voltage drop across the resistors, which we showed earlier, down to 0, which is expected. So for the second experiment, you put an ammeter in parallel with a resistor, and what you'll see is that the current will actually choose the ammeter, because in this example, the ammeter has 0 resistance, so right, the current will choose it. If you calculate the voltage drop across the resistor, you'll see that it's 0, and this makes sense because you want to go across the ammeter. And if you calculate the resistance in the previous circuit across each component, you'll see that you get 48 ohms, 102 ohms, and then 0 ohms for the wire and ammeter. And this makes sense just because the ammeter rounded that 0.02 value, so it didn't properly. You would be dividing by a higher value, or yeah, by a higher value, so you would get lower resistance values if you used a more accurate value for the current. So for the RC circuit, what happens is as the battery charges the capacitor, the brightness of the light bulb will dim over time. And after timing it, you get a 6.75 charge time and a 6.36 discharge time for a 10 ohm bulb. For a 20 ohm bulb, it's 10.43 second charge time, 11.48 second discharge time. And after calculating some voltage values and graphing the natural log of the volt over the initial voltage, what you get is a linear graph where if you take the natural log, right, the equation reorients itself so that the natural log of delta V over delta V naught is equal to negative T over RC. So you can calculate RC, which in this case is 5.98 seconds, which is very close to the expected value of 6 seconds. Some sources of error there could have been from rounding by the ammeter or the voltmeter, and then improper timing by myself. So what if we were doing this in real life and used an actual ammeter instead of the ideal simulated ammeter? So an actual ammeter does not have 0 resistance like the virtual one does, right? The circuits would end up having slightly less current because of its resistance, although it is a very low resistance. And then if we were using a real battery to charge a capacitor and there were no resistor, right, the calculation would predict a 0-second charge time for the battery capacitor circuit. But this isn't true because we know that real wires have an internal resistance, so it wouldn't charge in immediately.